I think we get old, you get senile, you don't remember what we had for breakfast. I know I had for breakfast, but I can't remember, did we really cover this? Rationalizing the denominator. Some of you probably had this in high school, and some of just came in, and you might have been taught that this is bad. This is not bad. It's a radical in the denominator. As a number, it's perfectly fine. As an answer to a problem, it's fine. If you're working on a problem and it's sitting there, well, it's a problem, and you want to get it out of the denominator. That's what rationalizing the denominator is about. X, some variable, it's likely that you'll need to get it out of the denominator. So we need to know how to do this. But again, I just want to emphasize this whole idea that there's something wrong with this. It's just, there's a reason for it. It's historical and it's not really valid anyway. So how do you get rid of square root of 2 in the denominator? Well, you want to multiply by square root of 2 in the denominator, so this will be 2. But you can't just multiply this by any old thing. You have to multiply it by 1. That was the identity property we talked about on Thursday. Well, how do I make this 1? There we go. So these are perfectly equivalent versions of some number. You might want to think of it as like, well, 1/3 is 2/6, right? It's the same number, it's just you can write it in different ways. Now, one student asked, maybe this is a homework problem, how do you deal with this? Well, it's the same idea, just a little more work. We want to multiply this by, well, 4th root of 2. Well, if we multiply it by the 4th root of 2, that's 4th root of 2, 4th root of 2. We're going to have 4 of these. We're going to get 2. But of course, we have that same problem here. This number we're going to multiply has to be 1. So I'm going to use the 4th root of 2, and the 4th root of 2, and the 4th root of 2. And how would we write that? Well, we could write that as 9 4th root of 2 cubed, which is 8. Questions about this? Other homework problems? If anyone has a question? Yes?
Oh, no, just this one. Why is it only 3 times instead of 4?
Because we have 1 to begin with,
Oh,
and we want 3 more.
oh, thank you.
Is that clear?
Yes.
You can kind of make it a general statement if you have like some number, I'll just put 5 here in the denominator, and you have n, you're going to have to multiply by this to the n minus 1 to get rid of this. Yes?
Couldn't you also turn the 2 to the root of 4 to 2 to the power of 1 over 4?
Can I say it again? Repeat.
Can't you turn 2 to the root of 4 to 2 to the power of 1/4?
Yes,
So would that be, and then like,
that's just another way of saying it.
so would that be an acceptable answer?
Over here,
Yes.
you could write this as 2 to the 3/4, absolutely.
Well, can we also just move the 2 to the 1/4 up and then multiply it by the 9, so it would be negative 18 to the power of 1/4?
Okay. As I told you, my hearing's a little deficient, and that was pretty fast. Say again, what do you want, were you talking about this problem?
Yes.
Okay.
So now that we have 2 to the power of 1/4 on the denominator,
What's that, 2?
yes.
2 to the 1/4, yeah.
Now we move the 2 to the 1/4 up and then multiply it by 9, making negative 18 to the power of 1/4.
Okay, you can do that. But what was the next part?
Would it be negative 18 to the power of 1/4?
I don't know where that came, negative 18.
Because when you move the 2, doesn't it become a negative?
I don't know where the negative came from. There's no, the only negative could be in the exponent, but,
Oh, okay.
so this is like 3 squared. I don't know where 18 comes from. If you want to come up and show me, I just don't understand.
Well, I was just like, in calculus, my teacher told me that like whenever you move something across the fraction line, it becomes a negative.
Yeah, that's true, but here's the trick. That doesn't really get rid of the radical in the denominator, which is, you know, I mean, this is perfectly valid,
Okay.
right? It just, it isn't what this problem is asking for. They're trying to show you, they want you to say, how can we get rid of this? You see, you have a negative here. That tells you this is 2 to the negative 1/4. That's 1 over 2 to the 1/4. And you see, you still have.
Okay.
Now, actually, it doesn't matter for numbers, but if you're dealing with variables, it could still be an issue. You might want to get it into the numerator. So, the radical. All right. Any homework questions? If you think of one after the break, it's also a good time to interrupt. All right. So, those of you who have good memories, back to Thursday, we're not getting started quite yet. Well, remember I had some kind of, pardon the expression, brain fart, having to do with the laws of exponents when applied to negative numbers. And I want to talk about that. I looked in the book. I was wondering, well, how does the book deal with this? And what they just say is you have something like a through 1 over n. They just say, well, a has to be greater than or equal to 0. Actually, greater than 0. They just dodge the question entirely. But I want to talk to you about it. It's one of those areas where you're not going to get a nice formula. You're going to actually have to think. So let me kind of guide you through what you might have to think about. So first, let's do something easy. Say what's negative 8 to the 1/3, or the cube root of negative 8. Anyone? Yes.
-2.
Yeah, it's -2. The key piece of wisdom here is when this is odd, no problem with negatives, right? An odd number of, an odd root, well, it's going to have a negative, and that's going to end up negative. Now, before we go into how to deal with this for an even, I just want to show you something that you need to look at. Squared 1/2. Okay, let's think this through. So -4 squared, that's 16. 16 to the 1/2, that's the square root of 16 times 4. Okay, good. Now let's look at -4 1/2 squared. Okay, now we're not going to do complex numbers for another few weeks. If you haven't seen them, just take a deep breath and don't worry too much. But the square root of -4, we call that 2 times pi. Pi is the square root of -1. And when I square that, I get -4. Well, that's just what happens when you do this. But this should make you wary of the laws of exponents, because if I were to just, there's a law that says a to the n to the m is a to the n m. Well, if I do that here, I get -4 to the 1, which is -4, not 4. So apparently this law of exponents doesn't work if the root is even and the number is negative. That's what you have to watch out for. So I guess the best advice I can give you is when you see something like this, think it through. Don't just apply this law willy-nilly. You have positive numbers, you have odd roots, 3, 5, 7, no problem. But otherwise, you have to think about it. I don't know why I threw this in, but can you guys read? Yes?
Is there an I? Is there an I with 2?
That's the letter I. As we'll see later in the course, we define the letter I as the square root of -1. Okay, so you don't have to worry about that now. That'll come later. And all the existential angst that goes with it. Wait, how do you multiply a number by itself and get a negative? Right? Don't worry about it. Are you a CS major?
No, I don't see it. I don't see it.
What's your major?
Entrepreneurship.
Oh, entrepreneurship. Wow, this will not matter at all. See, if you're an electrical engineer, you'll live and breathe this, or a physics major. But maybe there's some application in business. Okay. Any of you guys run into this online thing called Quora? Okay. For some odd reason, a lot of students like to post their homework problems if they can and get someone else to do it. And try to help but not do the homework. There was this question, y equals square root of 36x squared not plus or minus 6x? That was the question. Why is it not? Well, I don't know if we went over this detail. When we write something like this, let's say x squared equals 4. What are the solutions to this? Plus or minus 2, right? Has 2 roots, two solutions. So some people think, well, okay, So x equals square root of 4. This should be 2 or minus 2. And in fact, in high school, when you first get this, they might have said, yeah, the square root of 4 could be 2 or minus 2. But in mathematics, this symbol means the positive square root. So I could write this, that would be correct, plus or minus the square root of 4, which is positive 2. Right. So here, you might think, oh, well, maybe, so it's 6x, right? But it's not. It's not. Because x could be negative. So the correct answer is 6 times the absolute value of x. That's what this is. Simplify. Okay. All right. Take a breath. Yes?
If x was negative, wouldn't that make 6 negative as well because they are all together? If they're polar stuff, it would be negative 46 if that was
6 is 6. 6 is positive.
right, it's multiplied by x.
Well, if it's multiplied by x here,
Right.
and x is negative 1,
Then it would make it negative 6.
it could be negative 6. But if I plug in negative 1 here, I get the square root of 36, which is always positive 6.
Right,
Under this symbol.
but when we write our answers, we wouldn't write 6 absolute x,
If I said simplify this, this is the right answer. Because we have to make x positive for this to work right. Because this has to be positive. This is a positive number, x squared is a positive, and I'm getting the square root of it is a positive. The positive square root of this number is always a positive. This is more a notation problem you have to think through than a complicated math thing. It's just the way, just the fact that this always means the positive square root of whatever's in here. So we started looking at polynomials. I think I'm going to quickly go over all the stuff we ran across at the end of the last class. Didn't get very far, but I thought, why? We're going to talk all today about polynomials. Why are polynomials so important? Polynomial being something that looks like this, some constants, a's, why are these so important in math? You've already learned about polynomials to some degree back in high school. Equals x plus 1. This is a polynomial. It's a very simple one. Since the exponent here is 1, this is a degree 1. We even give this a special name, a linear term. Well, one of the things that's really great about polynomials is if you're doing something with math, you're doing science, you're doing economics, and you have some data, and you want to try and fit a curve to that data, you can always use polynomials to get some curve that models these points as close as you want. Now, some of you have maybe taken statistics, and you've already run into something called linear regression. Is that familiar to some people? You have a bunch of points, and you want to model it by a line. So you can do that. But not all data really wants to live that way. Some of it wants to move around. And you can always model any function with a polynomial. Now, as an example of this, I want to just mention in passing. So I'm sure most of you have seen calculators. And maybe you've run into sine, cosine, tangent before, maybe not. Maybe you've run into exponential functions, tangent units. You might think, how does the calculator, which really can only do simple math, it can only add, multiply, subtract, and divide, how can it figure out these functions? When I was in high school and college, in college, we saw the first handful of calculators come out. But how do we deal with this? Well, we just have a book with tables that someone had calculated for us, and we would look up with sines and cosines and tangents. But these little guys, they can calculate. The way they do that, in the case of, say, a sine wave, well, one thing nice about a sine wave is it's very symmetric. You really only need the points from here to here, which is 0 to 90 degrees, or 0 to 5/2, if you like radians. You really only have to know something about this curve. Well, you also, you can break this up into pieces. And each of these pieces you can model with a polynomial. And you probably know these calculators, they'll give you like a number out to at least 10, maybe 16 different digits. So that's how they do it. So, very important in math, science, and other fields. That's why we're learning about it. I thought I'd give you a little background. Maybe someone's done that before, maybe not. All right. So let's, with that in mind, let's go through all this stuff again. Again, there's some vocabulary that we need to know. These A's here, they're constants. Well, they are constants, but they're called coefficients. The first coefficient is important. It's called the leading coefficient. Probably the most important thing about it is its sign. Is it positive or negative? You have some polynomial where it's, say, let's say 3x, doesn't matter, third, fifth, whatever. One thing you know is, for large numbers, this is going to just go off into outer space. If, on the other hand, negative, it's going to go down. These are what we call the end behavior of a polynomial. Now, In the case of negative numbers, it's going to depend on whether this exponent is even or odd. In the case of an odd number here, in the other direction, it's going to go in the opposite direction. And one thing that tells you about that's important, if it goes down here this way and it goes up here this way, it's going to cross the axis at some point. Now, what do we call that when it crosses the axis? So root, thank you. Root. Sometimes we call that solution a zero. We call it a zero because this is where this is where y equals 0. Now, if it's even, say something like, you're probably familiar with y equals x squared in the parabola. Well, it might have 1 0. We add a number to it. Might have no zeros. We say, we subtract here. Might have 2 zeros. Okay. So even polynomials don't always have a real root. Odd degree polynomials always have a root. Okay, so that's the leading coefficient, and it tells you a lot. The largest exponent is called the degree. And again, I just mentioned whether that's odd or even makes a big difference. Each of these combinations of a coefficient and x to some value is called a term. This is just vocabulary that we're going to use, and you need to know what it means. And think of this as x to the 0, 1. This is called the constant term. Because there's no x there. This can be 0. All right. All right. So there's some things we need to know how to do with polynomials. The first and probably hopefully the easiest is we need to be able to add two polynomials. So here's an example of x to the 4th plus 3x squared minus 2x plus 1. And I want to add that to 4x squared 4x cubed plus x squared plus 3x plus 5. And of course, the key is to line up like terms. Like terms. That is, terms with the same exponent. So I'm going to write minus 2x as plus minus 2x. That's going to keep me from making a silly mistake. And I'm going to leave a place here, 0x cubed, because I'm going to have an x cubed here. And I'm just gonna write this the way I would do an addition problem. Now, I just have to carefully add the coefficients. Right, here 5x to the fourth, 0 plus 4 that's 3, 4x cubed, 3 plus 1 is 4x squared, minus 2 plus 3, that's just x, plus 6. A few practice problems and you'll all be experts. So that's adding a polynomial. Subtracting a polynomial, same thing, only here we would subtract the coefficients. I'm having a small problem here. I am using fogger on my glasses. This is kind of moist today. Let's see. The next thing we need to be able to do is to multiply two polynomials. If we're lucky and we only have two terms, we can use this clever device called FOIL. First, outer, inner, last. So first, that's these two. So 3x squared times x cubed, where we're just going to add the exponents, multiply the coefficients. We get 3x to the 2 plus 3 or 2/5. That's the outer, that's the first. The outer, well, that's 3x squared times x, that's pretty easy, 3x cubed. The inner, that's just x cubed, and then the last. And at that point, we would combine like terms here. We have 3x cubed and x cubed, so that just becomes 4x cubed. Well, that works if you just have linear term, two polynomials with just two terms. What do you do if it's more complicated? Well, so we're going to take this problem, x squared. Again, I'm going to write this plus minus x, not minus x, plus 4. Times 2x plus 3. So here we're going to use the same algorithm we use when we're multiplying two numbers out. I kind of have this knee-jerk reaction thinking, oh, everybody knows how to do that. But I do recognize sometimes these have had a deleterious effect on your education. You never learned how to do long division. See, this won't do long multiplication on polynomials. We have to learn this. So 2x squared plus minus x plus 4. And we write this down below, 2x plus 3. So first we're going to multiply 3 by this polynomial. We just have to multiply the coefficients. 2 times 3 is 6, minus 1 times 3 is minus 3, and 3 times 4 is 12. It's good when you're doing this, if there's a missing term, like this was cubed, good to leave room. Just treat it as a 0, because otherwise it's easier to make a mistake. All right, so here we have 2x times 4. That's going to go kind of 1 over, so that's going to be 8x. Negative x times 2x is going to be negative 2x squared, and 2x times 2x squared is going to be 4x cubed. And now we just add the coefficients. Minus 3 plus 8 is 5x. 6 plus minus 2 is 4x squared, and 4x cubed. A lot of students will make simple mistakes having to do with minus signs. I just leave this minus x. It's really easy to kind of, well, you get a minus 3 here, and then you have to think really hard. Minus 3 minus plus 8, what's that? So if it's reversed, 8 minus minus 3, that's where the mistake usually comes from. That's what I like, the idea of kind of attaching the minus to the coefficient here. Okay. Questions about this? There'll be some homework problems. You can practice it. If you have trouble, don't let it get away. This is really basic stuff you're going to need for this class, probably for many of you for the calculus, or for any other math classes. All right. You know, it's funny, I teach the class below this, the algebra, business algebra class, and I know we do division. I'm not sure where I think maybe later in the class we come up on dividing columns. We're not going to do that today. Well, I guess we could spend the whole class on that. All right. The next thing we want to talk about is factoring. So you probably know if you have a number like 48, you can factor it. You can factor it down to prime numbers. Prime numbers being 2, 3, 5, 7. If you don't know your prime numbers real well, you might, as a kind of an exercise, you can write down all the numbers. And then just, any all evens. 2 here, 3, make 9. 5 here, so we can eliminate that. It's good to kind of know, like, the first 100 or so prime numbers, because when you're factoring, sometimes you need to know that you can't factor a number. So let's just go. Good to be able to recognize a number as prime. If you don't, if you want some help with that, you can always ask me for some kind of exercise on how to do it. All right. So we can take a number like 48 and reduce it to primes. So first thing to look for is 2, right, because it's even. So then we have divide 48 by 2, we have 24. Well, that's still even. 12, still even. 6, still even. And 3. So those are the prime factors. You might write this as 2 to the 4 times 3. Just as we can do this with numbers, we can do this with polynomials. We can break a polynomial down to its prime factors. I guess I should say a word about what would we want to do that. Well, a very common problem would be something like this. We're looking for the roots. And if we can factor this, we can factor this into x plus a and, let me say x minus a minus b. We know that immediately that a and b are roots, right? Because they'll make it 0. So this is called a trinomial, because there are 3 terms, or 3 monomials. So how do we factor this? So there's a few different strategies. The easier strategies don't always work, but they're easier, so we learn them. The first thing to learn is that there are some very important patterns that you're not going to just need here, you're going to need under other circumstances. Whenever you see something squared 2 times those numbers, right, a squared plus 2ab plus b squared, this factors to a plus b squared. Very important pattern to know. Again, etch it into your memory or get a tattoo. Similarly, a squared minus 2ab plus b squared is going to be a minus b squared. Or, if you like, b minus a squared. It's the same thing. And probably the most important pattern to know is when you see square minus a square. We looked at this last week. A minus b times a plus b. So if you see in your trinomial one of these patterns, you're kind of done already. That x squared is 6. No, it's not going to work here. So our next strategy I want to pause for a second. I know some of you are probably like sitting there going, man, I could do this in my sleep, right? I just, did this recently. Not everybody is at that level. We're going to get on to more newer stuff, more complicated stuff pretty quickly. But we're going over it. Some people have been a year or two since they took a math class. We need a little refresher. That's why we're going over all this. Okay, so the next strategy, let's say pattern or pattern matching. Second strategy is reverse FOIL. For our particular example here, of x squared plus 5x plus 6, well, again, we want to find numbers that fit here. So how do we go about finding those numbers? Well, first of all, we've just got pluses here. These are just going to be plus. Our constant term here has factors. It could be 6, 1, or it could be 2, 3. So we can try them both. We say 6, 1, and now we just use FOIL. We check the inner, that's 1, and the outer, that's 7. That didn't work. Right. So we try 2 and 3. Inner is 2, outer is 3, that's 5, and so now we know we've succeeded. Now this is the easiest reverse FOIL you're going to run into. As soon as one of these pluses becomes a minus, things get more complicated. Now minus 6 tells you, well, one of these will be minus and one will be plus. That's how you get a negative down here. So that complicates things. If you have a coefficient in front of, a leading coefficient other than 1, that makes things much more complicated. Because now this has factors and this has factors. So you have to think, these factors are 2 and 1, these are 6 and 1, or 2 and 3, and you have to try all the combinations. And pretty quickly, it gets out of hand, and you don't really want to do it, and you want to use another method. So, I'm going to move on. Doing this pattern matching or reverse FOIL won't always work. There are trinomials that it's not going to work for. So, let's look at an example. Oh, I'll just make up an example. We want to factor that. Well, the next technique we're going to look at is called completing the square. This will always work. However, you will probably almost never use it to solve one of these. You still want to know how to do this because there are other circumstances other than trying to solve it, find the roots of a trinomial where you need to complete the square. The idea and where the name comes from is you think, well, okay, I've got an x here, got an x here. This has a coefficient of 1. I'm trying to make a perfect square here. So what I have is a 1 down here. But that's not what I have here. But that's okay. All right, so I can take this, I can say this is x squared. Well, actually, that's not going to work, is it? I guess I'm going to have to cheat here. 2x. So this is going to be x squared. This is going to be x. This is going to be x. That's where my 2x's come from. This will just be 1. So I have x squared plus 2x plus 1. Oh, but I have something left. Now I have this pattern here. So I have x squared plus 1, x plus 1 squared plus 2 equals 0. And from here, what I would do is I would move 2 to the other side. I would find the square root of both sides. X plus 1 equals plus or minus the. Unfortunate, I picked numbers that are going to come up imaginary. It's all right. It still works. And now I get x equals -1 plus or minus here, -2. And I have my roots. This will always work, but again, you're probably never going to use this strategy. The reason you're never going to use this strategy is, and again, this is going to be now the last technique we're going to use for factoring trinomials. It's called the quadratic formula. The idea is you take standard form for a trinomial, and you will apply this number 3 technique, completing the square. Yeah, I think I'm going to do it. If you've seen this before, I apologize. If you haven't seen it, it's worth seeing it once in your life. So the first thing we're going to do here is we're going to divide by a. So we get x squared plus e over a x plus c over a equals 0. And to complete the square, what we do is we take this coefficient, we divide it by 2, and we square it. So we have x squared plus b over a x plus, fill in c over a. So this value here is b over 2a squared. But we can't just add that to this side, we have to add it to both sides. Now we have a perfect square. This is x plus b over 2a squared. And I'm going to move this to the other side. B over 2a squared minus c over a. I find the square root of both sides. So I'm going to use this area here. X plus b over a equals plus or minus square root of b over 2a squared minus c over a. And I'm going to subtract b over a from both sides. I get b over a plus or minus the square root of b over 2a squared minus c over a. Now, what does this tell me? It tells me if I have a trinomial with coefficients a, b, and c, I can just plug them in, and I get my 2 roots. This may not look that familiar, but if you work this a little, you're going to see this is just negative b plus or minus the square root of b squared minus 4ac all over 2a, which is probably the form you're familiar with, right? Okay, so this tells me the 2 roots. And I can transform my x squared plus c equals 0 into x minus negative b plus the square root of b squared minus 4ac over 2a, and x minus negative b minus the square root b squared minus 4ac over 2a. So a little cumbersome, but it will always work. It will always give you the roots. There's a little extra information in here. This particular expression, b squared minus 4ac, tells you a lot about the solutions. This is 0. Well, you just have negative b over 2a as the roots. Double root. If this number is positive, two real roots. And if it's negative, you're going to get two complex roots. That's how to solve a trinomial. I think we're going to break now for a few minutes, and then we're going to learn a little more about factoring polynomials. So hopefully that will be new stuff. I'll be back in a minute if you have any questions. I'm going to make an announcement at the beginning of class. Told everybody, well, we play this one. And if you make arrangements, you say, well, I was full time. That's my issue. This is pretty cool. Okay, yeah, don't worry about that. You can turn it in either in class or online. All right, I want to pause the math for a minute. Talk about some mechanics. So there's kind of this conflict I have with the school. It's not a big conflict, but it's a little one. So there's something they don't want me to do. There's something they do want me to do. But the thing they don't want me to do, between us, I'm doing anyway. So, I think you're all familiar with HTTP, // This is my last name, SCHOENBRUN.com/USF. And if you go there, well, you'll have to click Math108. And if you go there, you will find all my notes in PDFs, and you will find links to my videos that I post. Now, when you look at the videos, at the beginning you'll see what we're doing. They don't always come out, hopefully. But 4 years ago, I did the same thing, and all those old videos are posted too. So if you go back and look at an old video, they're not as good quality as a better camera. The school would like me to put these on Canvas. My videos are on YouTube. And for various reasons, that's, I can't do that. So rather than not give you access, I'm breaking the rules a little here. I don't think, if you don't like me, report me and get me fired. That's all you can. But there it is. So anyone who needs, wants to look at my notes beforehand or after, want to look at the videos, you got it. Okay. Questions about that? A few people were asking me, you missed a class, this is one way to catch up. I assume everyone here knows about Canvas and about the homework on Canvas. As I mentioned, you can anybody has anything to turn in, you can turn it in at the end of class, I'll bring it down to the grader. Turn it in online, I guess it's easier. What else was I going to say about that? And just I'm repeating myself. Whatever date I put, it's like, well, if you're on top of the class, you'll turn it in then. But if you turn it in a week late, that's okay. If you need to turn it in later than that, contact me, we'll negotiate it. If you have a good reason, you got sick or I want you to do the work. I want you to do the homework for practice. Make sure you know the material so you can do well on the exams. Getting back to math, getting back to the last part of the class, Aiken pointed out that I kind of left something out when I was talking about completing the square. I left out the key. How do I complete the square? Well, I do this trick. I take this number, 5, I divide by 2, and I square it. But I didn't really explain why. I have to add it to both sides, this number. Why do I take this coefficient, the b, divide it by 2, and square it? Well, if you look at this pattern here, what do I have? Here I have, well, I might have a coefficient squared here, but then I have to do something else. But this is just 1, right? So that's my a, or x if you like. Here's my b, that's 5 over 2. So 1 times 5 over 2 times 2 is 5. I think I did that too quickly. Take 5 over 2, multiply it by 1, multiply it by 2, and I get 5. So that means this is that exact pattern, where I have x plus 5 over 2 squared here. And that's the key part of completing the square. The rest of it, you subtract 7 and you find the square root and all that is solving, but this is the completing the square part. This particular number, you have x squared and some coefficient on x, that's the number to use. All right, any questions about that before we go forward to the fun stuff? All right. here on, when we try and factor a polynomial, there are a bunch of different strategies. They don't always work, but they might. Well, here's a strategy that will always at least give you an approximate answer, which is if you have a computer system or one of these PI calculators, you can plug in your polynomial and you can say, where is a 0? And it will at least give you an approximation. So if you had some polynomial and make something up. And you plug it into the calculator, and it gives you some value, we'll call it R1. And you know x minus R1 is one of the factors here. And as I mentioned, we may actually have to do division today, but you can divide this out and get a lower degree polynomial that you can repeat. So that's a strategy for dealing with higher degree polynomials that you want to solve. But sometimes you have a higher degree polynomial that you can solve exactly. So here's an example. The strategy here is called grouping. It works if you have an even number of terms. Well, it can work with an even number of terms. And what you do is you try and group them either groups of 2 or groups of 3. You factor each of these separately. So what are the common factors of x to the 4th and x squared? X squared and the common factors of 4x plus 4 are 4. Thank you. And since this is a religious institution, you then pray. Wait a minute. That didn't work. That didn't work at all. Wrong problem, I guess. Let me take a look. How do I get that? No, that's not right. It has to be 4 squared. Oh, that's what I'm missing. Sorry. All right. Where was I? All right. Wrong problem. You factor each group, and you hope they have a common factor. This made-up problem, we got lucky. Well, now I can see immediately, this is x squared plus 4, kind of using the reverse of the distributive property. It's really the distributive property, times x squared plus 1. Is that clear how I did that? If these don't match, then it doesn't work. Here's stuff. So that's grouping. Now, at this point, we have x squared plus some number. And unfortunately, that cannot be factored in real numbers. It can be factored if you allow imaginary complex numbers, but this is kind of the end of the line here. So you can also see that there will be no solution in reals here, right? These all have to be positive. 2 positives is a positive, can't be 0. There's no way to make that 0. But you can factor this polynomial. So that's one strategy. The last strategy we're going to go over here for factoring a polynomial is called, well, using the rational root theorem. Okay. Has anyone here heard of the rational root theorem? Okay, I wouldn't have expected that unless you've taken this course before. Let's take a polynomial that's factored. And I'm going to cheat here. I'm going to kind of multiply it all out, but I'm not really. I know that after I'm done multiplying these three, I'm going to get an x cubed. And down here, I'm going to get a c. And, there's some other terms here that don't matter. So we look at this and go, You can see our roots here are minus a, minus b, minus c. This is the product of those, right? So if I have some polynomial that looks like this, I might be able to guess a root because it might be one of these factors. And that's the idea behind the rational root theorem. We're looking for rational roots, not irrational square root roots. So let's take a look at an example. Okay, I want to factor this, and I'm hoping it has a rational root. Look at the constant term, and that tells me that the only possible rational roots are factors of this: 1, 3, minus 1, and minus 3. Let's see if any of these are roots. And let's start with the easy ones. Let's plug in 1. 1 minus 3 minus 1 plus 3. Oh my gosh, hit it right off. I got lucky. See, this is 0, right? That means 1 is a root. So that tells me x minus 1 is a factor. Now, turns out the rational root theorem is a little more complicated. I'm just going to describe it to you. If I have a polynomial, I'm going to call it b x to the n plus q. The rational root theorem says that the only rational roots to this equation, the only possible numbers we can use as a factor, are going to be factors of p over q. So, for example, if we had 2x to the n plus, well, let's make it more complicated, 6x to the n plus 15. Well, there are a lot of possibilities. All right, we've got 15 over 6. We want to look at the factors here. 3 and 5, and 2 and 3. Well, 1's So what are the possible roots? There's 1, -1, 3, -3, 5, -5, 1/2, -1/2, 3/2, -3/2, 5/2, -5/2, and you've got 3 here. There's a lot of them. 1/3. We already hit 1, 5 plus or minus 1/3 plus or minus 5/3. And then this could be 6, right? So plus or minus 1/6. This seems kind of tedious, but hey, it might be our only shot at factoring this. 1/6. 3/6 is a half, so we covered that already. 5/6. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 12, 13, 14, 15, 16, 17. There's 20 possible rational roots. We can plug each one of them in, make a lot of work, and see if it's 0. If it's 0, we have a root. Now, what do we do about that? Well, we've got one root. It tells us one factor. In the case of our example here, so we know it's x minus 1 times some polynomial of the lower degree. So how are we going to find this polynomial? Well, now we're going to have to divide. So I think we're going to, I think we do long division in this class. Does anyone here not know how to do long division of polynomials? Perfectly okay. You might have learned something called synthetic division. Does anyone know synthetic division? Right. Either is fine. I'll go over synthetic division, right, quickly. If you want to learn it, it's a little more convenient. All right, so just using long division, I'm going to leave room for x squared, because that's really helpful. So, okay, just like long division with numbers, x goes into x to the 4th, x cubed times. -3 minus -2. Bring this down. -2 2x squared -2x. No, this is cubed. Sorry, cubed plus 2x squared. 0 minus 2 minus 2x squared plus x minus 2x squared plus 2x. Well, there you go. I can't do this on the board so easily. I made a mistake, and I'm not going to go find it right now. Maybe when I'm done with the synthetic division, I will. All right, how do we do synthetic division? Since we're dividing by x minus 1, we write 1, and we write down the coefficients. 1 minus 3, 0, minus 1, 3. So I bring this number down, I multiply, times minus 1, and I add. 1 times minus 2 minus 2 when I add. 1 times minus 2, minus 3. 1 times minus 3 is minus 3, and I better get 0. In other words, the remainder 0. These now represent the coefficients. So I end up x cubed minus 2x squared minus 2x minus 3. Does that tell me what I went wrong here? I think I was supposed to get minus 3x here. Could have been. Nope. Homework assignment for me. Okay, so now, what do I do with this? I have one factor, x minus 1. It's a cube. I can try the rational root theorem again. What are the possible roots here? They're the same as before. 1, -1, 3, -3. All right, let's try 1 again. 1, minus 2, minus 2, minus 3. That didn't work. How about minus 1? Minus 1, minus 2, plus 2, minus 3. That didn't work. I swear I probably made a stupid mistake. But let's see. Maybe my notes will tell me what I'm supposed to get. According to this, 3 was a root. And 1 was a root too. All right, let's try 3. 27 minus 18 times 2 is 36. No, that can't be right. Guess I should have mapped this problem out a little more carefully. All right, I'm gonna against my own better judgment, I'm gonna shut up and I'm just gonna do the problem from scratch because that's a good way to deal with this. It kind of gets messed up. Start from scratch. All right, let's do the fourth. 3x cubed minus x plus 3. So let's try 3. So that's 81 minus 81 minus 3 plus 3. So x minus 3 is a factor. So let's divide x minus 3. X to the fourth, minus 3x cubed minus x plus 3. X cubed, x to the fourth, minus 3x cubed. X plus 3 minus 1. Minus x plus 3. So this is x minus 3 to the x cubed minus 1. X cubed minus 1 equals 0. Rational root theorem tells me possible rational roots are 1 or minus 1. 1. 1 minus 1 is 0. So I divide this by x minus 1, what do I get? So x squared, x cubed, is x squared minus is positive, plus x squared minus x plus 1. So my factors are x minus 3, x minus 1, and now x squared plus x plus 1. I can try the rational root theorem, and I can see right away 1 and minus 1, neither of them turns 0. So to factor this, I'm going to use the quadratic formula. So what is the quadratic formula? Negative 1 plus or minus the square root of 1 minus 4 over 2. Negative 1 plus minus the square root of minus 3 over 2. These are complex roots, and that kind of solves the problem. All right. I don't feel like I've done justice to this topic. I feel like I was a little off today. I apologize. This is hard work, right? You have all these ways to deal with it. You can kind of skip reverse FOIL and complete the square by just always going to the quadratic formula when you have a trinomial. If you have more than a trinomial, you can try grouping and try the rational root theorem. Yes?
So when we're finding roots, can we just plug in, find the graph on our calculators and then find the zeros that way?
So, yeah, I think I kind of mentioned that in passing. You can put the graph on and you can use the, you know how to do this, you know. Come to office hours, I'll show you. You can use the calc feature. The problem there is it's going to give you it may give you an exact number, but if it's a root, like square root of something, you know, you might immediately pick it out, like 1.41, square root of 2. You might figure that out, but it won't always. In a practical situation, like you're doing physics, that's probably going to work, right? Yeah, so that's in the real world, that's the alternative, is to use a numerical method, which your calculator does for you. There's one other kind of obscure area that I thought I should fill in before I let you guys go. We talked about some patterns. Let's try one of them. B squared A plus B minus B. There are two other patterns that the book mentions. I wouldn't expect you to memorize them, but they're useful sometimes. A cubed minus B cubed, A cubed plus B cubed. And I believe A minus B A squared plus AB plus T squared. And I believe this is A plus B times A squared minus kind of easy to get this confused. You don't have a 2 here. You can check these just by distributing. We actually ran into this here, right? We think x cubed minus 1, and we got x minus 1 and x squared plus x plus 1. That's also can be useful. I'm confused here. I feel the end of the class. The end of the class is 4:25. We're gonna get to go early today because I'm done. I'm done with factory. Enjoy the hot work. Work together if you need to. Ask questions. Bring them in on Thursday.